In this video, we work a second example problem in which we solve an initial value problem with the Laplace transformation. Here, the initial conditions are specified at t equals 0, and the differential equation has constant coefficients. So we've got a third order differential equation, y triple prime minus 2 times y double prime plus y prime equals this exponential function. And we've got three initial conditions since it's a third order differential equation, and they're all specified at t equals 0. Now, the way we start all of these problems is we let the Laplace transform of little y equal big Y, because we don't like to just start using notation without telling people what that notation means. I always start there. I tell my students, if you do nothing else, please write this down. Let the Laplace transform of y of t be big Y of s, and then we're going to take the Laplace transform of the differential equation. Okay, now the Laplace transform is a linear operator, so you can just apply it to each term separately. You can factor out the constants. And then from the theorem that we talked about in the last video, we can take the Laplace transform of the third derivative. So for the third derivative, you start with an s cubed, then you let the powers of s decrease by 1 until you have an s to the 0. So you're going to have 4 terms there. And then this will be multiplied by the Laplace transform of little y, which is big Y. And then the order of the derivative increases as we go from left to right here, and these are all little y of t. So you have little y evaluated at 0, and little y evaluated, or little y prime evaluated at 0, and then y double prime evaluated at 0. Those are from the initial conditions. We're going to substitute those in a moment. So that's the Laplace transform of y triple prime. Then we're going to subtract 2 times the Laplace transform of y double prime. Since it's a second derivative, we start with an s squared. Then we'll have an s to the first, and then an s to the 0. Now remember, if this is the third derivative, we're going to have 4 terms. This is the second derivative, we have 3 terms. In general, for the nth derivative, we have n terms. That can help you keep track if you're not sure that you're doing this correctly. So we have an s to the second, s to the first, s to the 0, and then we multiply by the Laplace transform of y, and then we have little y at 0 and y prime at 0. Again, you've got the Laplace transform first, and then you are using those y's from the initial conditions, and the order of the derivative increases as you go from left to right until you run out of terms. So that's that first, this is the first one, and then we have the second one right there. Now we want to do the third term, Laplace transform of y prime, that's s to the first minus s to the 0 times something. And we're going to multiply the s to the first by y of s, and then we've got little y at 0 there. And that equals 2 times the Laplace transform of e to the 2t. Here a is equal to 2, so that's e to the at. According to our sheet, that is the Laplace transform of e to the at is 1 over s minus a. Now again, I guess I didn't write it down. Maybe we should write this down. The Laplace transform of the nth derivative of y is s to the n times y of s minus s to the n minus 1 times little y at 0. And then eventually you have the n minus 1th derivative evaluated at 0. That's what we have applied there. And then the Laplace transform of e to the at is 1 over s minus a. Now these are on your table of Laplace transforms, but we use these so often that I highly recommend that you commit these to memory because they're going to come up over and over again. A lot of students just refer to that sheet until they don't have to refer to it anymore. I think that's a great approach. So now we're going to substitute in our initial conditions in this equation. Y of 0 is 2. Y prime of 0 is also 2. And y double prime at 0 is 5. Okay, now let's simplify. So I have s cubed times y of s from right here, minus 2 times s squared times y of s from there, plus s times y of s on that last term. and I've just factored out y of s from all of those guys. So I took care of that one, and that one. And then everything else is just a constant times some power of s. So let's just write those down. So I've got minus 2s squared there, minus 2s, minus 5, and then we're distributing a negative 2 here. So I have negative 2 times negative 2s, which is going to be positive 4s. Negative 2 times negative 2 is positive 4. And then we're subtracting 2. And that's equal to the right-hand side, which is 2 over s minus 2. So after taking the Laplace transform of the differential equation and then substituting in our initial conditions, so we're substituting values of y of 0 all the way up to the n minus 1th derivative at 0. Then you end up with this equation in y of s. You want to take this equation now and solve it for the Laplace transform of the function you're looking for. So we're solving for y. I would factor this as well. These all have a factor of s in common. So I've got s times s squared minus 2s plus 1 times y of s there equals this 2 over s minus 2. And then I want to add terms to the other side. So this guy, if I add it to both sides, will give me a 2s squared on this side. Then I've got a negative 2s plus 4s is positive 2s. Subtract that from both sides. And then you've got negative 5 minus 2 is negative 7. Negative 7 plus 4 is negative 3. So I've got negative 3. Add that to both sides. You're going to have positive 3 on the right-hand side now. And we're really close to getting y of s by itself. I would continue to factor that. This is s minus 1 times s minus 1. So you could write that as s minus 1 squared times y of s. I'm going to leave myself a little space over here. Now we want to get y of s by itself, so I'm going to divide out s times s minus 1 squared. But rather than taking this and then dividing by that and then having to do the algebra that way, I'm going to remember that dividing by something is the same as multiplying by 1 over that expression. Dividing by 2 is the same as multiplying by 1/2, for example. So if I want to divide this out, I can just take this term and multiply by 1 over s times s minus 1 squared, because that's the same thing. And then this guy, I will actually divide by s times s minus 1 squared. And after simplifying, we've got y of s by itself, which is what we wanted. So I've got 2 over s times s minus 2 times s minus 1 squared. And then here, I've got the same thing. Question might be, can we use partial fractions for something like that? Well, we can definitely use partial fractions for something like that, but sorry, I got ahead of myself. My brain started on a tangent that was not actually where I wanted to go. The question is, can we factor this numerator? Because if we can factor this numerator and reduce with something down here, we might want to do that. Well, s is clearly not a factor of this. What about s minus 1? Is that a factor? Now remember what we said about polynomials. We said that s minus 1 would be a factor if s equals 1 is a root. So if I plug in s equals 1 here, I get 2 times 1 minus 2 times 1, so that's 2 minus 2, which is 0, plus 3. So s minus 1 is not a factor of this, because when I plug in s equals 1, I don't get 0, I get 3. Okay, so that doesn't factor further. And we can just do this. Now, some students choose to get a common denominator for this whole thing and just do partial fractions once. I recommend doing partial fractions twice. The partial fractions aren't that difficult. And if you get a huge fraction that represents the sum of these two, it just tends to make the partial fraction decomposition method slightly more complicated. Now, again, you're saying, why are you doing that, Ms. Townsend? The reason why we're doing that is because we're trying to write this in a form that we have in our table. And we don't have factors in our table where we've got 1, 2, 3, 4 linear factors where one of them is repeated, or 2 linear factors and one of them is repeated. So in order to write this in a form so that we can take the inverse transform, we need to use partial fractions. Then we will have a form in our table for every term. There may be a little bit of algebraic manipulation necessary when you might have to multiply by a well-chosen one or something like that. But that would be okay. That would not be too bad at all. Okay, so let's do that. Let's use partial fractions for this guy. So I've got 4 linear factors. This one and this one are not repeated. So I'll have a constant over s, and then I'll have a constant over s minus 2. And this s minus 1 squared will have 2 different terms in the decomposition. So I'll have a constant over s minus 1, and then I'll have a constant over s minus 1 squared. Now I had to go outside of the lines here because I ran out of space. But that's the partial fraction decomposition for this guy. Now, in order to get the values of A, B, C, and D, to find those, I will multiply by the LCD. So these guys reduce, and these guys reduce. The s's reduce. The s minus 2's reduce. The s plus 1's, or one of those will reduce, and then both of them reduce on that last one. So we end up with this. Just a 2 equals a times s minus 2 times s minus 1 squared plus b times s minus 1 squared plus c times s minus 2 times s minus 1 plus d times s minus 2. Now we can solve for some of these constants by choosing values of s that cause each of these factors to be 0. So let's choose s equals 0 first. If s is equal to 0, then this term would be gone because I'd have c times 0 is 0, and then this term would be gone because I'd have d times 0 is 0. So those guys are gone. Oh, b times 0 is 0 as well. So if s is equal to 0, the only term that does not disappear is this one. So I just end up with 2 equals a times 0 minus 2 is negative 2. And then I have 0 minus 1 is negative 1. Negative 1 squared is positive 1. So multiplying by positive 1 doesn't do anything. So a is 2 divided by negative 2, which is negative 1. Okay, now pick another value of s that causes one of the factors to be 0. Let's choose s equals 1. If s is equal to 1, this term disappears and this term disappears because I'd have a 1 minus 1 squared. That's going to be a 0. We'd have a times 0 is 0. Here we have b times 0 is 0. Then we'll have c times 0 is 0. But if s equals 1, that one does not disappear. So we can solve for d. On this side, we have a 2. If s is equal to 1, we'll have d times 1. And then we have 1 minus 2, which is negative 1. So d is negative 2. And then we'll use s equals 2 over here. If s is equal to 2, this guy is 0, and this guy is 0, and this guy is 0, so we can solve for b. The right or the left-hand side is 2 in all of these cases, but if there were s's over here, we would plug these s's into the left-hand side as well. So if s is equal to 2, this is the only term that does not sort of disappear. I have 2 times b, and then 2 minus 1 is 1. 1 squared is 1. So I have 2 times b equals 2. So b equals 1. And that's it. Those are the only values of s that would cause the factors that we have to be 0. Notice that we got a, b, and d, but we didn't get c. So we need to find c. One way that we could find c is to distribute and collect like terms, and then use the linear independence of the powers of s in order to set up a system of equations for a, b, c, and d, and then use these to find the value of c. So that's one way of doing it. Or we could just pick a value of s that's not on this list. Now, normally I would choose s equals 0 or s equals 1, but we've already chosen those because those values of s cause the factors to be 0. Now you just pick a different value of s. I would choose, let's just choose s equals 3. Why not s equals 3? So in that case, we'd have 2 equals a times 3 minus 2, which is 1. And then you'd have 3 minus 1 squared. So that's going to be 2 squared, which is 4. Plus b times 3. And 3 minus 1 is 2. 2 squared is 4. Plus c times s is 3. 3 minus 1 is 1. And then 3 minus 1 is 2. And then we have d times s, which is 3. And 3 minus 2 is 1. Okay, so we've got this equation, and we actually know the values of a, b, and d. So let's substitute those in. If a is -1, this becomes -4. And b is +1, so I end up with 4 times 3, which is 12. C is unknown, so I just have 6c. And then I've got 3 times d, and d is -2, so it's going to be -6. And if I simplify this, I've got 12 minus 6 is 6. 6 minus 4 is 2. So I end up with 2 equals 2 plus 6c. So 6c must be 0. So that means c must be 0. Okay, cool. So we've got a, b, c, and d. Those are the values that we need to put in these numerators so that a over s plus b over s minus 2 plus c over s minus 1 plus d over s minus 1 squared will give us this guy over here. So that was the first one. Now let's do partial fractions for the second one. Now that second expression looked like this. 2s squared minus 2s plus 3, all divided by s times s minus 1 squared. We end up with a constant over s here, and then a constant over s minus 1 here, and then a constant over s minus 1 squared here. Because we've got 2 linear factors, one of them is repeated. Remember how the repeated factors work. If this was an s minus 1 cubed, you'd have 3 terms in the partial fraction decomposition. And you'd have s to the first, or s minus 1 to the first, s minus 1 squared, s minus 1 to the third. If that's k, you'd end up with k terms in the decomposition. If they're linear factors, you just have constants in the numerator. Okay, so we're trying to find the values of a, b, and c now. And we multiply by the LCD as we always do. And the LCD is always the original denominator. S is reduced, the s is reduced here, s minus 1's reduced here. One of the s minus 1's will reduce there, the s minus 1 squared reduced there. So we end up with 2s squared minus 2s plus 3 equals a times s minus 1 squared plus b times s minus 1 plus c times s. And we're going to do the same thing that we did last time. We're going to choose values of s that cause our factors to be 0. So I'll choose s equals 0. In that case, I end up with 2 times 0 squared minus 2 times 0. So those are going to be 0. Plus 3, so that's 3, equals the expression over here on the right. If s equals 0, this is b times 0, which is 0. And that's c times 0, which is 0. So these guys are gone, and we just end up with this guy. So we end up with a times 0 minus 1. That's -1 squared. -1 times -1 is +1. So I just get a equals 3. That's really nice. Very convenient. When s is equal to 1, we have 2 minus 2, which is 0, plus 3, which is 3. And if s is equal to 1, this guy is 0, because we'd have 1 minus 1 squared, so it's a times 0 is 0. Then we'd have b times 0 if s is equal to 1, so that's 0. And then I have c times 1, so it's just c. That's really nice too. Didn't even have to solve even a very, very simple equation. Okay, so we did not get b, and that's because of this repeated factor of s minus 1 squared. So we need to pick another value of s. You can pick any value you want. I'll just pick s equals 2, because why not? 2 squared is 4. 4 times 2 is 8. And then we have 8 minus 2 times 2. So 8 minus 4 is 4. 4 plus 3 is 7. And then I'll have a times 2 minus 1 is 1. 1 squared is 1. plus b times 2 minus 1, which is 1, plus c times 2. And we know that a and c are both 3, so this is 3 plus 2b plus 6. So we end up with 7 equals 9 plus 2b. So subtract 9 from both sides, and then divide by 2 to solve for b, and you get b equals -1. Okay, great. So now we know the partial fraction decomposition for this guy. So y of s is the sum of the partial fraction for the first term plus partial fraction decomposition for the first term plus the partial fraction decomposition for the second term. And I'm using the term very loosely, just saying expressions that are added together. I'm thinking of each of those as a term. So this term and this term in quotes. So this guy can be rewritten this way, where a has a value that we found earlier. A is -1. So we have -1 over s. And b is divided by s minus 2, and b happened to be 1. C is divided by s minus 1. So that's from that, that's from that right there. And c is equal to 0, so we don't have one of those. And d is equal to -2, so we have -2 over s minus 1 squared. Okay, so that's the partial fraction decomposition for the first guy. And then for the second one, we have a over s, where a is 3. Plus b over s minus 1, and b is -1. Plus c, which is 3, over s minus 1 squared. Now I've got some like terms. These guys are like terms. 3 minus 2 of those is going to give us 1 of those. And then we've got some like terms there. 3 minus 1 of those would give us 2 of those. So this is 2 over s plus 1 over s minus 2. So I took care of these two guys and this one. And then for these two, I'm going to have 1 over an s minus 1 squared. And the only one I did not include yet is this 1 over s minus 1. Actually, we have something in our table for each of these guys. And I'm just going to write those down. The Laplace transform of 1 is 1 over s. The Laplace transform of e to the at is 1 over s minus a. The Laplace transform of t times e to the at is 1 over s minus a squared. The Laplace transform, so that's all we need actually. I was thinking we had 4 terms, so I needed 4 of them, and I actually only need 2 or 3 because we used the second one twice. Okay. So between those 3, and of course you're using them backwards, the inverse transform or inverse Laplace transform of these 3 guys are given by these 3 functions for the right values of a. We're also using the linearity property of that inverse Laplace transform. So y of t is the inverse transform of 2 over s plus 1 over s minus 2 plus 1 over s minus 1 squared minus 1 over s minus 1. And that's given by this. We get 2. And then here, I'm going to get an e to the at where a is equal to 2. Here, a is equal to 1, and here, a is equal to 1. So this is going to be e to the 2t. Here I have t times e to the at where a is equal to 1. So e to the t minus e to the at where a is equal to 1. So y of t equals 2 plus e to the 2t, and I'll probably factor out that e to the t. Okay, great. So that's how we do that. We let Laplace transform of little y be big Y. We take the Laplace transform of the differential equation, we substitute in our initial conditions, and we end up with this equation involving y of s. We solve for y of s. Just do some algebra. You get this by itself. And then you've got to do partial fraction decomposition. So we did partial fraction decomposition twice, once for this and once for this. Took a little while. Then eventually, after doing all the partial fractions, we ended up here with y of s equaling this, which simplified to this. Then once you have that version of y of s for which every term has an inverse Laplace transformation or an inverse Laplace transform in our table of Laplace transforms, then we go ahead and take the inverse transform. So we're computing the original function that we're looking for by taking the inverse transform of y of s. Okay, now, if you take the first, second, and third derivative of this and substitute into this equation, if I've done everything correctly and I haven't made any mistakes, we should get t times, or 2 times e to the 2t. And if we evaluate that function at 0, we should get 2. If we take its derivative and evaluate it at 0, we should get 2. If we take the second derivative and evaluate it at 0, we should get 5. This function is the solution to this initial value problem. And that is different. It's a very different method than the method that we learned earlier. The other method would have been to solve the corresponding homogeneous equation using the y equals e to the m times t, because it's a constant coefficient equation. Then we would solve for y sub p, probably using method of undetermined coefficients. That'd probably be the most efficient way to do this rather than using variation of parameters. Then you'd have y sub c equals, or y equals y sub c plus y sub p, and it would have 3 arbitrary constants in it, c sub 1, c sub 2, and c sub 3, because it's a third order equation. You can say, how do I find the arbitrary constants? Well, you'd use these 3 conditions to get 3 equations and 3 unknowns, and you'd solve for c1, c2, and c3. Or you could do this. Now, one downside of this is that you don't know the general solution to that differential equation. But if you're not interested in finding the general solution to the differential equation, if all you want is a solution to the initial value problem, the Laplace transformation method is very nice. It gets you to the answer pretty quickly.